This is a review of Part 1 of Digital Systems. Part 1 aims to get you familiar with digital systems, including in the labs where you become familiar with building digital systems. You might not be able to build your own digital systems for harder problems, but you're going to start to understand how digital systems work and what they can do and how other people build them. So you should be comfortable reading other people's relatively straightforward digital systems by the end of Part 1. For lack of a better word, we have simple digital systems, or ones without memory, formerly known as combinational logic. And then we can build anything by combining combinational logic together with flip-flops. And as soon as we add flip-flops, we then start to talk about finite state machines. So the first part of Part 1 discusses our combinational logic. After that, we introduce flip-flops and can talk about finite state machines which use combinational logic between the flip-flops. So in terms of the actual logic gates, we just have to understand combinational logic, which is the first part of Part 1, and then we just have to understand flip-flops. And then, of course, when you put the two together, we always think in terms of finite state machines. And they were introduced in a few examples here. And Part 2 of the course is going to go into detail about the theory and the design of finite state machines. The key characteristic of digital systems is that the wires carry only two voltage levels. Either the wires are at 0 volts or they're at some supply range voltage such as 5 volts. And we talk about that as being either on or off or high or low or 0 or 1. The advantage of talking about zeros and ones is that that can bring mathematics into it. And once we have mathematics, we can talk about representing numbers in the binary system, and that then makes it easier for humans to design circuits to do what they want. It also allows mathematics to be applied in the shaping of the actual implementation of certain logic functions, which we don't cover very much of in this course, but we do mention Boolean algebra there as well. In terms of the theory of combinational logic, we have got our truth tables and we've got Boolean algebra. In terms of the implementation, we can buy discrete logic gates and wire them up by hand, or we can use an FPGA. And inside an FPGA, we have got lookup tables, which are multi-purpose logic gates, so to speak, and we've got flip-flops. And remember, any digital system can be made from combinational logic and flip-flops. In the olden days, if we wanted to build a digital system to achieve a certain task, we would have to work out how to connect up various logic gates together to achieve that task. We can do the same thing on an FPGA by using VERILOG to describe exactly the logic gates that we want connected up. But these days, we can take a much more powerful option, and essentially we describe in VERILOG the behavior that we want, and the software that synthesizes the design onto the FPGA, Quartus in our case, is smart enough to work out how to go from the described behavior into the actual logic gates. It's not a complete mystery because we know how to do it by hand. Given the described behavior, we first of all implicitly generate a truth table. So we list all the possible inputs. We work out from the behavior what the correct outputs are. From this truth table, we can then do something like a sum of products form to represent it using Boolean algebra, which can then directly be represented using logic gates. The power of a hardware description language such as VERILOG is the reason we need to learn it for this course. If we were to just design logic gates by hand, we would not be able to build anything at all complicated in this course. We really need VERILOG to be able to have for our final project the building of something as complicated as a computer, for example. In a nutshell, once we understand that digital systems just carry information in using zeros or ones, and we know that we can build simple circuits from basic logic gates, the first part of the course is about understanding how to describe such circuits using VERILOG. That then allows us to implement our circuits on an FPGA and see them operating. Initially, we can treat an FPGA as a black box and just say that, well, it does what we tell it to do using VERILOG. However, a good hardware engineer needs to understand how they can shape the actual circuit being built using VERILOG. Some implementations of the same function are more efficient than others. Some have certain properties that others lack, and so forth. So this understanding starts with understanding how FPGAs work, and we build on that by looking through a variety of examples and seeing how our VERILOG code gets translated into actual hardware configurations inside the FPGA. The real power of digital systems comes as soon as we introduce flip-flops. As soon as we have flip-flops, we can have counters, which are very intuitive to understand circuits that just count 1, 2, 3, 4, 5, for example, and the current number, can be stored in flip-flops and incremented at each rising edge of the clock. So while flip-flops have a clock input, and we always say that at the rising edge of the clock, the input to the flip-flop gets photographed and passed on to the output of the flip-flop just after the rising edge. While we could in principle connect up any output from a logic gate to the clock of a flip-flop, we do not do that at all in this course. In the olden days, you'd sometimes do that, but these days we focus on what's known as synchronous design. Every single flip-flop in our design is going to be driven by the same clock. And a clock, of course, is just a square wave that is used for synchronization. It keeps the beat. We think of combinational logic as doing the actual work, and at the rising edge of the clock, the work done by each combinational logic unit is photographed and passed on to the next unit for further processing, just like an assembly line. With a clock and this assembly line concept, we are naturally led to consider streams of numbers. Basically, any design is going to be processing a stream of numbers. The stream is delimited by the rising edge of the clock. And if we want to understand what's going on, we now have to consider the time domain as well. And that's when timing diagrams become important. So timing diagrams were introduced for combinational logic, but they are really needed as soon as we start to talk about flip-flops and the time-varying nature of our digital systems. The remaining topics in the first part of the course try to convey a variety of ideas at the same time. So parallel to serial and serial to parallel conversion, firstly, is a nice simple application of flip-flops. It also helps emphasize the number string concept where we're sending streams of numbers over time. And it also helps show you how VERILOG can be used to build actual basic units that can be put together to form more complicated digital systems. Part of digital systems is communications. We're forever sending data from one point to the other. When we connect our FPGA to sensors and actuators, we have to communicate with them. And so once again, we have the problem of how to communicate between different devices. How can we send instructions to a sensor and have it send back readings? How can we send instructions to actuators and have them carry out something in the real world? Lecture 13 looks a little bit at the actual implementations, different ways of implementing the same basic operations in VERILOG, and we're able to get a greater throughput by using pipelining. And when we're crossing clock domains, we have to use synchronizers to avoid the probability of a flip-flop becoming metastable. So with this as background, I'm now going to go through each individual lecture and try to summarize the key points of each lecture for you. Lecture 1 simply introduces digital systems. If you're ever after more information, then you can ask me directly for recommendations. The textbook Digital Design, A Systems Approach was the standard textbook prior to us moving online, and that would be the first book I would recommend if you wanted something to complement this course. I've also asked the library to order in some electronic books which you can access from anywhere in the world. At the end of the course, these big questions should be self-explanatory. What are digital systems? Why do we care about them? How do we design them? And how do we implement them? That's what we're going to learn about in this course. As mentioned at the start of this video, digital systems convey information using only two states, off or on, or 0 or 1, or low or high. The way we can visualize this is think of a switch connected to a light. You press the switch, the light goes on. You release the switch, the light goes off. You're transmitting one bit of information. If we want to transmit 2 bits of information, then we just use 2 wires with 2 switches at one end and 2 lights at the other. I can then send one of 4 messages to my friend in the other room. If the switches are in my room and I have them both off, my friend sees 2 lights are off and they know that that's one message, 0, 0. If one switch is on, the other's off, then my friend will see 1 light's on, 1 light's off, and know that I was signaling the binary number 10 to him. Keep in mind though that if I'm sending a sequence of messages, then how will my friend know when I'm actually sending a message and when I'm just transitioning between one message and the other? And that's why later on in part 1 we talk about using clocks for synchronization. We need to have some way of knowing when the numbers on the wire are a legitimate message and when the numbers on the wire are just transient things that we don't really want but are just an artifact of having to transition from one message to another message. Digital circuits are so much easier to design and build than analog circuits that most things these days are digital. As a positive feedback loop, because digital circuits are popular, then transistors are mass produced, so it drives down the price, and so there's a positive feedback cycle whereby most things these days are just done in the digital domain. Digital systems both process information and also transfer it. And you might think the transfer of information is straightforward, but if you have a lot of information to transfer and only a few wires, you need to have some protocol for doing that. Computers process digital information and they also transfer digital information, such as sending the pixels to your display to be displayed on your screen, for example. All of these things, all digital systems, can be built out of 2 types of devices, logic gates and flip-flops. Logic gates are how we implement truth tables, and flip-flops give us memory. It's important to emphasize that you learn by doing, especially this course, which is a hands-on course where you actually build digital systems. The only way to learn properly is by actually trying to build systems and learning from your mistakes. Lecture 2 looks at logic gates and combinational logic. So remember, the 2 things that make up digital systems are combinational logic, that provides our instantaneous transformations in an ideal world. In the real world there are delays. And our flip-flops give us memory. If we are building a digital system by hand, then we use logic gates to implement combinational logic. If we're using FPGAs, then inside FPGAs are lookup tables, which are configurable logic gates, so to speak. And we're going to focus on logic gates and combinational logic over the next few lectures. At an even lower level, combinational logic and flip-flops, they themselves are made just using field effect transistors. So it's quite remarkable, by just using one device, so no resistors, no capacitors, no inductors, no diodes, nothing except field effect transistors allow us to build complex digital systems. Now there's a small lie there. You do need to have bypass capacitors for the power supply and so forth, But in principle, all we need to make digital systems are FETs. We will look at this in the second part of this course. We have spoken about understanding digital systems in terms of switches and lights where we can send a message to a friend, but we can also process that information. We can put two switches into a logic gate, and then the output is going to be some function of the two switches. So if, for example, I want the output to light up my light only if both my inputs, both my switches are on, then I need to use an AND gate. And so the truth table for an AND gate is that if both inputs are a 0, the output's a 0. If one input's a 0 and the other's a 1, then the output's still a 0. And only if both the inputs are a 1 is the output a 1. So you should just visualize in your mind connecting up two switches to an AND gate, connecting up the output to a light, and the only way that that light is going to be on is if both those switches are on. Similarly, if we connected up our switches to an OR gate, then that light is going to be on if one or the other switch is on. These are our basic logic gates, and if we ignore timing delays and complicated things and only look at ideal gates, then their behavior is completely described by the truth table. They're just functions telling us, given a certain input, what the output is going to be. It is important to know the named logic gates, their symbols and their truth tables, and you can find this information in the Wikipedia or in a book or a variety of other sources there. So go and have a look at that information and make sure you're familiar with it. You should be able to understand why any truth table can be implemented using only NAND gates. Partly because we need it in VERILOG, and partly because you may need it in subsequent courses you take at the university, it's important to become familiar with Boolean algebra, which allows us to manipulate combinational logic using mathematical symbols and expressions that are more familiar to us. Remember that combinational logic is simply some logic gates where you can connect switches on one side and a light on the other side, and the light will be either on or off depending on the settings of the switches, and depending on the combinational logic, you can have the light going on and off in response to different combinations of the switches as defined by a truth table. A simple example is an AND gate where the output is on only if both of the inputs are on. If we want to have precise control over what gets synthesized, we can describe our combinational logic using Boolean algebra in VERILOG. How this is done is illustrated on the video here on this page. Remember, if you see wire x is equal to something, that's a shorthand notation for first defining the wire and then using an assign. If the combinational circuit is relatively straightforward, then often we would use a case statement, which essentially allows us to simply tell VERILOG what the truth table is, and the synthesis tool will figure out how to implement that truth table using logic gates. The video here gives an example of how that's done. The most powerful way to use VERILOG is by describing the behavior that we want to achieve. So we don't specify the exact logic gates using Boolean algebra. We don't specify the truth table using a case statement, but instead we simply describe the truth table that we want implemented by using what essentially looks like the C programming language. We give an algorithm for how to compute the output given the input. Now, it's essential to realize that this program is not executed on the FPGA at all. In conceptual terms, the synthesis tool generates the truth table by applying that algorithm to all possible inputs. Given the truth table, it can then proceed as in the case before. From the truth table, it can figure out how to implement that behavior using the lookup tables on the FPGA. It's also important to realize that what may look like complicated functions, such as taking the cosine of a number, multiplication, addition, exponential, using complex numbers, etc. That all can be done using combinational logic because the output is a fixed function of the input. As an advanced note, sometimes if the number of input wires and output wires is too great, then we would prefer to implement the circuit using a finite state machine to save real estate. But nevertheless, in theory at least, all these operations can be done using combinational logic. The video in the slides gives an example of how we can describe the behavior, and we can see a bit of it on the screen here already, where we're describing combinational logic because it's an always at star. If it's always at pos edge clock, that suggests we're going to have flip-flops. This suggests we're going to have combinational logic. And we describe the output by using a for statement and an if statement. So this is the one time when you can understand Verilog, just like the C programming language. This is an algorithm that, given an input, computes an output Y. And from this algorithm, Quartus is able to deduce what the truth table is and then how to implement this combinational logic using lookup tables on the FPGA. When told there are 3 different ways of doing something, it's very natural to ask, well, which way do I pick? And that comes with practice and experience, but roughly speaking, if you want precise control, you'd use Boolean algebra. If you're given a truth table or a truth table is easy to implement, then you'd use a case statement. If it's easier to describe the behavior you want using an algorithm, then you could take the behavioral approach. Timing diagrams are introduced early on in this subject because they're extremely important for understanding what's actually happening at the electronics level. Remember, these digital circuits, although we think at a higher level in terms of zeros and ones, they're being implemented as an analog electrical circuit using field effect transistors. The timing diagrams are equivalent to going to the lab, taking an oscilloscope and putting the probe at the output of a logic gate and looking at the waveform there. So the timing diagrams we draw are idealizations of the exact voltages you will see if you put an oscilloscope into the digital circuit that you're interested in. Timing diagrams are an essential part of this course, so if you haven't watched the video in the slides before, it's highly recommended that you watch it. In Quartus, there are 2 types of simulations. As the circuit gets more complicated, or as the FPGA gets more complicated, it takes longer and longer to do the more sophisticated simulation. In fact, with the Cyclone 5 FPGA that's on our DE1 SoC boards, you can't actually do the timing simulations anymore because the FPGA is just too complicated. The faster simulations are functional simulations, which assume that the logic gates are ideal. That means that the logic gates don't have any delays in them. This gives us an idealization of our circuit. The advantage is that the simulations are much faster. The benefit of that is that if we had made a silly mistake somewhere, it's going to be caught early. So if doing a gate level simulation takes 2 or 3 days, which it could do if you have a really complicated circuit and you test it through hundreds of different cases, then you don't want to have the situation where you make a small change to your code, you compile it, that might take a few hours, you then run your timing simulations, that might take a few days, then you realize, oh no, I made a trivial mistake. The aim with digital design is to catch mistakes early. The earlier you catch mistakes, the cheaper it is. Functional simulations allow us to catch mistakes very quickly. Sure, some more sophisticated mistakes make it through, but at least we catch the simple mistakes early on. To learn a programming language quickly, and that's our aim here, we need to become good at 2 things. First, we want to become familiar with some standard ways of writing code. So when you're learning a new language, as in a spoken language, you don't have to learn all the complicated ways of saying things. You just learn the simple, safe ways of saying things. So in terms of writing our own Verilog, we're just going to be taking very standard, simple approaches to that. But then the other side of the coin is we want to be able to understand what the Verilog simulator is doing so we can understand in principle any Verilog code. So in some sense, it's like we not only want to speak Verilog, we want to be able to listen to Verilog and understand it. And so we're going to have a look today at how Verilog simulators actually simulate the code. Not in a great amount of detail, that will come later in the course, but we want to understand that Verilog simulators essentially keep track of simulation time. They try to solve for all the voltages in the circuit or the digital states, are they zeros or ones? They try to solve for that at a particular time instant. Once everything's stabilized, they then move on to the next time instant. This is the key concept to get across in lecture 4. Practice is essential, and perhaps the most convenient way of learning Verilog is by using these online Verilog simulators. They make it very easy for you to type in some Verilog code and run it and see what you get. Some people like this website here, HDL Bits. It's essentially a collection of small problems that you actually type in your Verilog solution to. It then runs it through a Verilog simulator and checks whether or not you've got the correct answer. When we drew the timing diagram for a combinational logic circuit, the timing diagram has got time represented along the horizontal axis. And when we run a Verilog simulator, it's also essentially computing the same timing diagrams. That's its job. So it has to keep track of time. It has to know what time it's up to. It has to then analyze the circuit at that particular instance in time. And then when everything's stable, it can then say, well, at this time, this position here has got this voltage, that position there has got that voltage, and it can report it all using a timing diagram. Precisely, if you use Model Sim with the waveform viewer, you do exactly see the timing diagram. Otherwise, without a graphical interface, we can use display statements to print out the values of the voltages at certain places. And of course, being digital, by voltages, I simply mean 0 or 1, on or off. Actually, Verilog allows two other possibilities. We could have a don't know, and we can also have a high impedance, which we'll worry about later. Verilog, when it's being simulated, is a concurrent programming language, meaning that many different parts of the Verilog code can be executing at the same time. So I like to explain this by saying we've got a lot of friends, each friend has got one job to do, and they can all be doing their jobs at the same time. Although it takes physical time for your friends to do jobs, they are essentially just computing what's happening in the circuit at a specific instance in time. So even though an actual digital circuit will immediately get the right answer, so to speak, it might take 1 second or 2 seconds of your friend's time to actually compute the correct answer, because it's simulating the circuit, it's not the actual circuit. And so that's why the Verilog simulator has to keep track of simulation time. It says, okay, we start at time t equals to 0. What's the state of the circuit? And then it has to follow through it from the switches at the input. It then has to say, well, this Y is a 0, that one's a 1. Then it flows through this AND gate, which produces a 0 at the output, which then flows through this other logic gate. It's got to do lots of computation. And that might take physical time for the simulator, but it's trying to work out what the state of the circuit is at time t equal to 0. And so it can do many calculations trying to work out the state. It does not advance simulation time at all until we've got convergence. Once it's figured out exactly what the state of the circuit is at time t equals to 0, then and only then can it advance simulation time and move on to simulating the state of the circuit at the next time instance. And remember, all its job is to produce a timing diagram. So when you are asked to do a timing diagram for a circuit, that's all a Verilog simulator is being asked to do, to produce a timing diagram for a digital circuit. There must be some mechanism in Verilog to move on to a new instance in time, and that's through the delay operator, which uses dare I say in modern language, a hashtag, or just hash in computer science language. So in this code in front of us, a #1 means a delay of 1 unit of time. A #2.7 means a delay of 2.7 units of time, but we actually have to know what the resolution of the simulator is to know whether or not this will be rounded off, and we'll come to that later. And #5 is a delay of 5 units of time. So depending on the resolution, when we run this, then at simulation time 0, nothing happens. At simulation time, well, technically it depends. If we assume x changes at time 0, so this gets called. But if we assume that's the case, then at time 1, this gets displayed. At time 3.7, that's 1 plus 2.7 is 3.7, this gets displayed. And adding 5 to that, we then get this line being printed out. The caveat about the timescale is explained here. The first number, 1 picosecond, are the units of time. So a #1 will be 1 picosecond. The following number, 1 picosecond here, is the resolution. This is the smallest increment in time that Verilog can take. So if you ask Verilog to increment by 1.2 picoseconds, well, it can't, because its increments can only be in units of picoseconds. So 1.2 will be rounded down to 1 picosecond, and 1.5 will be rounded up to a 2 picosecond delay. The real-time variable, so variables with a $sign in front of it are special, they're system variables, so to speak. Real time contains the time including decimal points, and time contains the rounded off version of time. You really do need to run these yourself and see what you get and think about what you get, and only then will you really understand what's going on. If we change to a 10 picosecond unit, that means #1 becomes 10 picoseconds. So #1.2 becomes 12 picoseconds, and #1.5 becomes 15 picoseconds. The best way I know of figuring out what a new language is doing is by putting lots of print statements everywhere. Then you can check what's happening at each point in the code. Every time we have an always block, we think of a separate friend being assigned to do this task. So here we've got 1 friend, 2 friends, 3 friends, and a 4th friend is going to run this initial block here. So with 4 friends, 4 things can be done at once. And when we run this code here, we can see when this friend does something, when this friend does something, and when this friend does something. So run this code and figure out what's being executed when. A key feature of Verilog or any concurrent language is that if you've got 2 friends asked to do something at once, you've got no idea which friend is going to finish first. So in this code, we have no idea whether I am Fred or I am Wilma is going to be printed out first. Now, any given Verilog simulator might decide to implement this in a fixed order, but it doesn't have to. The Verilog standard says the simulator is free to choose which one to do when. That means our code should not depend on the order of execution, which cannot be guaranteed. This makes sense because when we synthesize our code, then each different block of our code, well, of course, we can't synthesize display statements, but if we had always at star statements describing combinational logic, then the combinational logic here is going to be one part of our digital circuit. The combinational logic here is going to be another part of our digital circuit, and they're both doing their job at the same time. They both have got electrons flowing in at the input and producing electrons flowing out at the output at exactly the same time. So we can't say that one of these blocks is going to be done before the other. Importantly, if we have a begin-end pair, then the order of execution is guaranteed to be sequential between the begin and the end. In behavioral Verilog, where we describe the behavior we want our circuit to have, it's very important knowing that we can write in, if you like, ordinary C, describing an algorithm, and it will be executed in sequence from begin to end. We should not use #0 ourselves, but other people do. It's a way of saying I've finished my job for the moment, let all my other friends do their job first, but when they're done, don't implement simulation time. I still have something left to do, but I want to wait for my friends to catch up. Like most programming languages, there are different ways of being able to repeat the same thing a number of times. We've got repeat loops, while loops, for loops, and forever. And be comfortable using any of them, and over time you will pick up your own style, your own preference for when to use which one. Number representation in Verilog is very important, and because we're working directly in hardware, we always have to specify the number of bits in our number. Now this happens in any programming language, but implicitly. When you define an integer in C, well, how many bits is it going to occupy in memory? Certainly not an infinite number of bits. There's an upper limit to the size of an integer you can store in an int in C. In Verilog, the way we specify the number of bits is by writing it out the front, and then we have an apostrophe, then we have a letter denoting what the base we're using. Are we using binary? Are we using octal? Are we using decimal? Or are we using hexadecimal? And then we write the digits normally after that. So B's for binary. This represents an 8-bit binary number, which is 00000101. If we leave off the number of bits, then although there's no agreed upon number, the Verilog standard says it has to be at least 32 bits, and so most simulators just use 32 bits. Often we do not want a 32-bit number, so sometimes you can get away with this lazy notation, but it's best to always be precise. A very useful feature of Verilog is that we can combine and split individual bits. And often we want to do this in hardware. I might have 8 wires coming in to a junction, and then I want 4 of the wires to go to one place and another 4 of the wires to go to another place. So I need to split them apart. Conversely, I might have 4 wires coming in from one device, 4 wires coming in from another device. I want to combine them to have 8 wires. And the way we combine things are using this notation here. And we can have over here, I am combining this number and this number. So 4 bits here and 4 bits here get combined into an 8-bit number. And here I'm splitting them apart. Given an 8-bit number, I can split it apart into the first 4 bits and the second 4 bits. At this point, I should emphasize I'm not going through every single slide, and always, if you want more information, you hit the down button to learn more about it, and if you want even more information, then either you look at one of the books I've referenced earlier on in the lecture series, or even better, just ask me for where you can find more information. In this particular case, if you'd like more information, then you just have to Google for it, and it's quite easy to find online material about Verilog. Here are some examples of what you can find describing the Verilog programming language. Lecture 5 is about tying up some loose ends with Verilog. So lectures 1 to 5 about digital systems are saying, well, this is what combinational logic is, this is how we implement it in Verilog, and here are some other things we can do in Verilog. A common mistake students make at the start of this course is that they put test benches into Quartus and wonder why Quartus gives them error messages. That's because synthesis and simulation are two very different things. Synthesis is when Quartus takes the Verilog code and implements it in physical hardware. It configures the FPGA to implement that circuit. Simulation is simply working out how that circuit behaves and displaying it for the end user so they can check that the circuit does what they intended it to do. The purpose of a test bench is to emulate hardware. Sometimes the circuits we make are used in very dangerous applications. We might have an FPGA controller at a nuclear power plant. We might have an FPGA controller in the latest military fighter jet. And we can't simply take our code, upload it to a fighter jet, get a pilot to sit in it and test it out, that's a very bad idea. So how can we test out our circuit without actually implementing it in hardware? And that's the purpose of having simulators. But simulators need more than just the circuit. They need to know what the input is to the circuit, and they need to be able to display the output for us. So the purpose of a test bench is to generate the inputs to the circuit for us. In very simple terms, if our actual circuit has got switches at the input and lights at the output, well, the purpose of our test bench is to simulate moving those switches, feeding the inputs into our circuit, and then being able to display whether or not the lights go on or off. Keep in mind the distinction between module definition and module instantiation. A module definition is when we define a chip. I like to think of it in physical terms. We're making a chip. It's got a bunch of pins on it. Some pins are input, some pins are output. What does that chip do? Well, that's the module definition. It defines a particular chip. In this case, it's just defining an inverter. When we go to use an inverter, we don't reuse the same inverter. If our electronic circuit needs 10 inverters, we have to buy 10 inverters. We don't buy one inverter and use it 10 times. Every time we buy a new inverter, we are instantiating our inverter, and we have to give it a different name. So we have an inverter called Fred, another inverter called Bill, because they're distinct inverters. They're two different chips. So we've got module definition and module instantiation. In particular, that means that module instantiation is not a function call. We are not calling a module. Never, never, never think in those terms. We are creating a new chip with each instantiation. For those of you who are familiar with inline code in modern C, you can think of module instantiation like inline code. So whenever we instantiate a module, we are taking the definition of that module and putting it right there in the module where we instantiated it from. In this example, when I instantiate this MFC, it means that I replace these lines with all the circuit here. Now this is a very simple circuit, but even if this were a very complicated circuit, I would literally just stick it right in here to replace all of that. Then when I instantiate another type of this chip, I do the same thing. I take all of this and just put that circuit right in here. Where do I put it? Well, this is what our connecting wires tell us, how we wire it up, how we wire this circuit into this circuit here. If you like to keep things simple, then you just follow this basic rule. Whenever you define combinational logic, you have to make sure that the output of the combinational logic you're defining is always given a value. Just stick to this rule and everything will be fine. So in this case, the problem here is that if A and B together are 0, 1 or 1, 0, nothing is assigned to C. So I need to understand this as creating hardware. Do not think of it like a C program. Think of it as creating hardware. It's combinational logic because that's what we get by default. Without a pos-edge clock, there's no flip-flop, so the only thing left is combinational logic. We're producing combinational logic, but the output, we don't know what the output should be if A and B are 0, 1 or 1, 0. A VERILOG simulator is going to say, well, that means I don't change C, because if this was a programming language, then if I don't modify C, it stays the same. But in hardware, we can't do that. I can't create a chip whose output magically stays the same for some values of C, but is different for other values. Why? Well, if you want to go into it, and the slides do go into it, they explain it for you, but I won't here, I'll just quickly summarize it. The problem is that depending on the past history of A and B, if I have 0, 1 coming in here, sometimes C might be equal to 0 and sometimes C might be equal to 1 by the rule that C doesn't change. If C was originally 0 and I have 0, 1 coming in here, then C has to be a 0. If C was originally a 1 and I have 0, 1 coming in here, then C would have to be a 1. But with combinational logic, which is the only thing we can create in hardware, the value of C has to be fixed given the input. That's what our truth table is telling us. So if I have 0, 1 coming in, there's only one possible value the output can be if I'm building digital logic out of combinational gates or lookup tables on an FPGA. And because in this case here, I can get different values of C coming out for the same A and B going in, because there's some sort of memory happening, I just can't build it using combinational logic. We've seen the display statement in Verilog. It's sort of the equivalent of a print statement. But as you get better with Verilog, you'll use display less. Display is really good for understanding how Verilog works, and sometimes you use it for quick things. But remember how Verilog is going to do many computations to work out what the waveforms are at a particular instance in time. And so at any point in your Verilog code, you can display X, but that X might just be the current value right now before all the friends have done their job and worked out what the final value of X is going to be at the end of that simulation time. So often you want to use strobe X. That says that, okay, print out the value of X at the very end of the current simulation time right now. And if you want that to be done whenever X changes, that's when you can use the monitor statement here. If you pick up a book on digital systems, you'll find that quite a number of chapters are often dedicated to special types of logic chips, like multiplexers and priority encoders and adders and so forth. And you might wonder, well, because we now have Verilog, I can just describe the behavior of what I want and Quartus will just figure out how to do it. Why do I need to know these building blocks? It's no longer 20 years ago when I had to solder things together by hand, and then I really did have to buy a priority encoder chip and a multiplexer chip and wire it up. Well, that's because we still want to have efficient designs. And if we lose sight of how our Verilog code is going to be implemented in the FPGA, then we lose control of the implementation. And we might be implementing a simple circuit in a very complicated way. And why does that matter? Because you might be making 1 million products. So your company needs to buy 1 million FPGAs. And if they could have bought a $1 FPGA, but because your Verilog code produced a very inefficient hardware design, they're paying $10 for their FPGA, well, you've just cost your company $9 million there. So understanding the hardware implementation of what you write is crucial. Also, a good way of learning Verilog is to practice by implementing these building blocks of digital systems, such as multiplexers and priority encoders. Remember, this is a summary, so I'm skipping some slides. I skip slides about adders, etc. A multiplexer is a fundamental building block, and it's a digital switch. So we have multiple inputs. In this case, I've got 4 inputs. I call it a 4-way. Each input contains 8 wires, so it's a 4-way 8-bit multiplexer. So the output is also going to contain 8 wires, and depending on the select wire, either A or B or C or D, one of these is going to be routed to the output. So it's a digital switch. I've got 4 things coming in, only one is going to be switched to the output. And we can do that with a simple case statement. Depending on the value of the select line, then out is going to be equal to either A or B or C or D. We don't think of this as a programming language where I copy A to out. I think of this in hardware as an actual chip. I've got 4 inputs to that chip and 1 output, and depending on what's on the select lines, one of these 4 inputs is going to be directly connected to the output. Literally, a piece of wire is going to go from the input to the output, and that connection can change internally. So it's a 4-to-1 multiplexer here. Another standard building block is a priority encoder, and it's a good excuse to allow us to introduce a case Z statement as well. So I won't go through it here, but try to understand how the priority encoder works. It's another good way of building up your VERILOG skills. This brings us to checkpoint 1, which I won't go through, but I am flagging we've now reached checkpoint 1 in this summary. Lecture 6 concerns FPGA architecture. There's an embedded video here that goes through using Quartus so you can physically see what the inside of an FPGA looks like. The slides afterwards then summarize the key points. Signals enter and leave the FPGA through the pins, but they go via the in-out buffers. There's configurable wiring inside the FPGA. Think of it as a road network, a switchable road network, where signals can be sent from A to B just by flipping the switches on the different roads. In the simplest possible terms, the only other thing we have are logic elements. Each logic element contains a lookup table and a flip-flop. Remember, these are the two basic ingredients we need to build any digital system. For convenience, these logic elements are arranged into groups. I like to think of them as an apartment building. When the logic elements are in the same group, there's high-speed wiring between them, for example. But in principle, we've got our input-output buffers and our logic elements. There's just this extra structure here of logic array blocks to try to simplify the wiring and allow the addition of some additional features, such as being able to perform high-speed addition using some extra features some manufacturers put into their logic array blocks to connect up the logic elements. We don't need to understand that point. There's a number of reasons for having input-output buffers. There are some advanced features which we won't worry about, but they're also there to be able to provide extra current to drive things, to provide protection for the FPGA, and also to convert between voltage levels, since the internal voltage of FPGAs is often lower than the external voltage. The reason we'll see later in the course, but to put simply, we want a lower voltage to reduce energy consumption within the FPGA, but when you connect to the outside world, you need to overcome noise, and a higher voltage can be beneficial. The configurable wiring within an FPGA is formally known as programmable interconnect, and you can just think of it as a grid of wiring, and at each intersection point we can determine whether or not to have a switch open or closed there. So when we use Quartus to configure the FPGA, a lot of that configuration is working out which switches are open, which are closed, and that determines how things are wired up within the FPGA. For reasons we don't really need to understand in this course, logic elements are grouped into logic array blocks. As you go deeper into the architecture, this becomes relevant, but we just accept this for now. Besides the input-output buffers, the other crucial element of an FPGA are these logic elements. They do the actual work. They contain the lookup tables and the flip-flops, as we discussed before. Normally, one logic element contains one lookup table and one flip-flop, and it can be figured to only use the lookup table or only use the flip-flop, or to use the lookup table fed into the flip-flop. So these logic elements themselves are highly configurable. If you become a hardware engineer, then you're going to need to know how different FPGAs implement things inside them. And so companies put out data sheets that describe their architecture. And by having a look at these things, no, you don't have to read them in detail, but having a quick look through them, you'll actually see some familiar diagrams now. You'll see they talk about programmable interconnect and logic array blocks and whatnot. So have a quick look at them to connect this course up to the real world. Closer to home are the viewers that Quartus provides us with. So we basically have got three views, two distinct types of views. The register transfer level view shows us at a high level what we told Quartus to do in VERILOG. So if we write a program in VERILOG, and we want to check that we wrote it properly, we'd look at the RTL viewer to check that what we wrote turned out to be the circuit that we were wanting to build. At this high-level view, we don't worry about individual wires. We can group wires and just say this group of wires carries a number. That's partly why it's called register transfer level. And we have access to these higher level building blocks we've been looking at before. In particular, you can have a multiplexer at the RTL view level. So an FPGA does not contain a multiplexer. It has to implement a multiplexer using lookup tables. But by having the RTL viewer describe our circuit at a higher level, where it can use addition, it can use comparisons, it can use multiplexers, and so forth, it allows us to check quickly that the code we entered is describing the circuit that we want to implement. However, that's not how the circuit's going to be implemented. Quartus is going to have to figure out how to take our circuit and actually implement it using only lookup tables and flip-flops. And the technology map viewer basically shows us how Quartus is going to implement that. Now we can look at two different stages as to how Quartus has implemented things, and roughly speaking, the main difference between these two is that it's possible for an extra level of optimization to have taken place. So sometimes the view we get is essentially the same in these two views. Sometimes some additional optimization has taken place. Quartus has figured out a smarter way of implementing the design, and then you might get some differences in the views here. This brings us to checkpoint 2. Lecture 7 is the first time we implement the flip-flop. Together with combinational logic, we can build anything digital using combinational logic and flip-flops. A flip-flop gives us 1 bit of memory. This slide shows us the circuit diagram for a flip-flop. We only look at D-type flip-flops. We have a clock, we've got a D pin coming in, a Q pin going out, and actual flip-flops also have a Q complement going out. The VERILOG code is straightforward. At the rising edge of the clock, we photograph the input and transfer it to the output. If we want to make use of Q complement, we can also photograph the input going through an inverter and being photographed and copied to Q bar. For the first part of this course, we remember to use this non-blocking assignment when declaring a flip-flop and nowhere else. We will explain what's happening later, but the short version is that this actually introduces an infinitesimal delay. So we say that this flip-flop is going to photograph the D pin at the rising edge of the clock, but the output is not going to be updated until just after the rising edge of the clock. This gives us an infinitesimal delay that will make sure that if we cascade these flip-flops to get a shift register, that it's going to function correctly. We only look at synchronous design in this course. We're always talking about the clock. The clock's something that's a little bit hard to motivate in advance. Once you've seen a few examples of how it's used, it'll just become natural. So I wouldn't worry too much if it feels a bit funny at first. It'll become natural once you see examples of how it's used, but the clock's there for synchronization, just like a drummer on a dragon boat's there to synchronize everyone. All our flip-flops are going to be clocked by the same clock. The clock is just a square wave. At the rising edge of the clock, all the flip-flops photograph their input, pass it on to the output, and we can see with this synchronous design technique, there's no limit to what we can design for our digital systems. On the DE1 SoC board, the clock is an external circuit. It generates a square wave that is fed into the FPGA via a pin that we can then access inside the FPGA. If we write a test bench, we have to generate the clock ourselves, and the standard way of doing this is with code that looks something like the following. We declare a register to store the clock in. We start off with the clock being 0, and it's important it's 0 and not 1. And then periodically we just toggle the clock. So if the clock was 0, it becomes a 1, and if the clock was 1, it becomes a 0. So this generates a nice square wave for us representing the clock. Why start at 0? This is a little bit of a technicality, but when a Verilog simulator starts, everything is initialized to the don't know state. So clock starts off life as don't know. When it gets assigned the value of 0, going from don't know to 0 is actually going to trigger a negative edge, which is okay because we don't respond to that. Had we initialized clock to 1, going from don't know to a 1 would be considered a positive edge, and that will trigger all our flip-flops right at initialization, and that's not what we want because otherwise have not yet been initialized yet. So it's not going to produce the results we want. It's a minor thing, but we should have our clock starting life at 0. So the first rising edge is going to occur after this delay here. Also, when we write test benches with clocks, it's important that we don't change things at the rising edge of the clock. Remember, flip-flops want to photograph things that are not changing. If a photograph photographs things at the rising edge of the clock, the input must not change at the rising edge of the clock. So when we change the input to our system, we need to make that change away from the rising edge of the clock. So we need to know when the rising edge of the clock is. So we need to see here, for example, the clock's going to have a rising edge at time 5, 15, 25, 35, and so on. For Quartus to make sure that our circuit is going to work, it has to know the clock frequency. But nowhere in Verilog code do we describe the clock. If we write a test bench, we generate a clock, but that's different from the code that Quartus sees. Quartus just knows that there's an input that we're treating as a clock, but it doesn't know that it really is a clock, and it doesn't know what frequency it is. So we have to tell Quartus outside of Verilog, and you use a .sdc file to do that, and you basically put one line in there that tells Quartus that this input pin to the top level module actually contains a clock, and this is its frequency. And you'll learn about that in the labs. The best way to learn is by practice, so enter this code into Quartus. If you've got a board, burn it to the board, even better. If you don't, write a test bench for it. Make sure you understand what's going on here. Another basic digital circuit is a counter. If we want to count from 0 to 255, then we need 8 flip-flops. Why? Because 2 to the power of 8 is 256, and we're storing the numbers in binary. The practice problems will talk you through old-fashioned ripple counters and the modern synchronous counters. Here's an example of a very simple synchronous counter, and it's going to it follows the canonical form of all finite state machines that we're going to emphasize in this course. So we have our flip-flops here. How many flip-flops? Well, that's given by the size of count. So we see that count has got 4 bits in here. So we've got 4 flip-flops here. At the rising edge of the clock, the flip-flops get updated with their new value. This is the canonical form we use. We define the new value with the next keyword here, and somewhere in our code we define what the next value is. For a counter, the next value is just the current value plus 1. Normally we would have to test if the counter's reached the number we're counting up to. Has it reached the number 9? If it has, we don't want to go to 10, we might want to go to 0 instead. So normally we have an if statement or an inline if statement here. In this case, because count is 4 bits, we're just going to let it overflow. Now it can't magically, once it gets to the number 15 and we add 1, it can't magically store 16 there. It can't grow an extra wire to use to store that number. So at 15, when we add 1, we just fall back to 0 because we're just keeping the lowest 4 bits of the answer here. For part 1, I'm going to show you by example finite state machines. I'm going to keep emphasizing the names of the different parts so you can recognize it. You might not be able to write your own finite state machines, but that's not the aim of part one. The aim of part one is for you to understand other people's finite state machines. Now we've made the transition from combinational logic to finite state machines, we need to understand the concept of number streams. So with combinational logic, all we think about are switches at the input and lights at the output, and depending on how my switches are configured, that'll determine whether the lights are on or off. With finite state machines, the output can now depend not only on the current input, but also on the past input, because the finite state machine remembers a state, and that state depends on past inputs. Every input that comes along can alter the state, therefore there's some dependence on the past inputs of the state. The other way we think about this is that we are processing a stream of numbers delimited by the rising edge of the clock that the next slides are going to emphasize for us. To help motivate this concept of number streams, let's consider the problem that one part of our FPGA wants to send numbers to be displayed on the display to another part of the FPGA. The display, of course, means the other part of the FPGA is going to send the numbers through a decoder chip to the 7-segment display chips, so we actually see them on the board. So we have to send numbers, and these numbers are changing. That's the key thing. Because they're changing, it becomes a stream of numbers. If I first need to display the number 2, and then the number 5 a bit later, then the number 7 after that, well, that's a stream. First 2, then 5, then 7. When we are dealing with streams of numbers, we need to know when to sample the numbers, because remember, when we change the number from 2 to 5, there might be some transient responses. We can't change all the wires instantaneously from the old value to the new value, so we need some mechanism of knowing when the values are safe to be read. And the simplest way of doing this is to just agree that we are going to read the values at the rising edge of the clock. That means we need to have a shared clock. Now, often in applications where you're connecting your FPGA to another device, it's actually inconvenient to use a shared clock. Then the problem becomes a lot harder. We'll worry about that later, where we introduce synchronizers and so forth. But for now, we're going to assume we have a shared clock. So one side of the FPGA wants to transmit a number, the other side of the FPGA wants to receive the number, but thankfully we have a common clock. All the flip-flops are being clocked by the same clock, and this makes life easier for us. As a human, if we want to send the sequence 1001 when we speak it, because voice is analog, I say 1, you get hit with some sound waves. Then there's silence, so you know I finished saying 1. Then I say 0, then there's silence. And so the silence is used to delimit these digits. But in digital electronics, a single wire, it's either 0 or 1. There is no silent state. 0 is not silent, it's 0. 1's not silent, it's a 1. And there is no third state, meaning I'm not saying anything. And so we need some other way of being able to delimit a sequence of numbers. And that's why we agree that we will use the rising edge of the clock to mark out the digits. So to send 1001, that means I need to arrange for the numbers first 1, then 0, then 0, then 1 to be on the wire at the rising edges of the clock. So at the first rising edge of the clock, there should be a 1 on the wire. At the second rising edge, there should be a 0. At the third rising edge, there should be a 0. And at the fourth rising edge, there should be a 1 again. And in this way, we agree that we have sent the number 1001 to the other side. To understand our proposed strategy, I believe it's useful to think in physical terms. I have got 2 switches and my friend has got 2 LEDs. One switch connects to one LED, the other switch connects to the other LED. One of the pairs of switches and LEDs is labelled data, the other is labelled clock. And then you can physically put yourself in the shoes of these 2 people. One person is sending numbers, the other one's receiving them, and make sure you understand how this system works. once you've done this, you should really appreciate the role that the clock is serving to delimit the digits. Often in our design, we do just use this simple system because we do want to send a new number at every rising edge of the clock. But in this case, we only want to send our numbers to be displayed perhaps once every millisecond, and the clock's going much faster than that. So we need some other way of knowing when we're actually sending information and when we don't want to send anything at all. And there are, like anything, many ways of solving this problem. In this lecture, we discussed two ways. One way is to use the idea of a start bit, and that's discussed in the slides. Another way is to have an additional wire, which essentially says, okay, I'm talking now, you'd better listen. And if that wire is off, then it says, well, I'm not sending you anything, so ignore anything you see on the data wire. Because remember, the data wire is either 0 or 1. It's not like a human voice where it's either speaking or it's silent and we can tell the difference. We don't know whether a 0 is silence or whether 0 is actually part of a number. So we can either use a start bit to signal the start of a new number, or we can use an additional wire to tell us when we're sending a new number. So this is described in the slides. I'm not going to go through it here in this summary. Like with any coding endeavor, breaking your code up into smaller blocks has got many benefits. When you write a small piece of code, in particular, if you're capable of seeing that code in one glance, which basically means it's only a few lines long, then it's much easier to check that it's correct. At the other extreme, as soon as that code gets longer than, say, 24 lines and overflows the page or whatever, it's actually very hard to check that it all works. You have to start breaking it up yourself when you're checking it. And if you're breaking it up mentally, well, why not break it up in terms of the actual software code itself? Furthermore, if you build small blocks, you can reuse those blocks in your other projects. If you have one great big long function that only does one specialized thing, you'll never reuse it again. If you break it up into smaller bits, each of those bits might be used in a number of projects, and reusing code again is one way of reducing the chances of having an error. If you've used code before, then you know it works. You can safely just use it in your new project. This lecture contains a fair amount of code that you just need to go through yourselves and to make sure you understand exactly what's happening. That includes writing a test bench to see what's happening, and if you have access to a board and there's something that can be tried out on the board, that's always to be encouraged too, although you don't need to. You can do everything using a simulator. A key point to emphasize when we talk about number streams is that there's the physical reality of what's happening on the wires, and then there's our interpretation of what's happening. So we don't actually send a 0 and then nothing and then a 1 and then nothing, because we can't send a nothing, as we discussed before. So a number will always be present on the wires, but in terms of our representation, we can agree that we only sample it at the rising edge of the clock. In particular, this means that if I'm feeding the numbers I receive into my 7-segment display, my 7-segment display is not going to flicker. It's not going to show a 1 when it received a 1 and then magically switch off again. That 1 is going to be displayed continuously because the wires are always conveying a signal on them. Just a reminder that all our flip-flops are going to be driven by the same clock. If we want things to go slower, we need to do it by not updating the output of the flip-flop at every rising edge. Examples of how this can be done will be seen in the lectures here, and in part 2 we'll learn physically how that's done, either via a chip enable pin on a flip-flop or via an external multiplexer that can choose whether to feed in the next value into the flip-flop or to feed the current value back into the flip-flop so it doesn't update at the next rising edge of the clock. Really spend your time going through this extended example of generating a number, sending it via parallel to serial, reconstructing it via serial to parallel, and displaying it on the 7-segment displays. So really go through this carefully, make sure you understand all aspects, and then you'll be in a very strong position for the second part of this course. Lecture 9 continues on from Lecture 8. We are designing a system that generates numbers, sends them to another part of the FPGA via parallel to serial, then serial to parallel conversion, then converts it to be displayed on a 7-segment display, then outputs it through the pins of the FPGA to the actual 7-segment display. So we see that the numbers really are being updated in real time on a DE1 SoC board. On the one hand, you are not expected to be able to write this code yourself. On the other hand, you're expected to try this code out and to understand every part of the code very well. You really want to understand exactly what's happening and why. A basic principle when you're developing a circuit is to develop a smaller version of it first. It's a lot easier to get a simpler version working and then make it more complicated than to dive right in and try to build the complicated version immediately. The other trick is to first design the circuit using a simulator and having a much slower clock frequency so that we can see what's happening more easily. That'll make more sense if you actually do it yourself. Having a 50 megahertz clock is just going to confuse things when we do our simulations, because we have to wait very many clock cycles for something to update. You can actually buy a chip that performs parallel to serial conversion. So every time we write a Verilog module, you really should be thinking in terms of you're designing a chip. And often those chips really do exist in the real world. Before we had Quartus and FPGAs and writing things in Verilog, we actually had to go buy these chips, wire them up, and then implement our design that way. For parallel to serial conversion, we need to know when to start the actual conversion. So I need to have a start input that signals when to start the conversion. What starts off simple can quickly end up being a bit more complicated. Okay, we have a start pin. When it goes from 0 to 1, we start. That's well and good. But what happens if it goes from 1 back to 0 to 1 again before we've finished our conversion? What do we do? And in particular, whenever you have a finite state machine, there's going to be very many possible combinations of the inputs, a lot of which you don't really want to consider. And so the trick is to say, well, what's important? What can I get away with by ignoring or by taking a default action? And in this case, and this comes with a bit of experience, but in this case, the easiest thing to do is say, well, once the start pin's gone from 0 to 1, I'm just going to send my data, and I'm not even going to look at the start pin until I've finished sending my data. And so then we don't have to worry about what happens if the start pin changes while we're sending data, because we just ignore it. We continue sending our data. Everything is a finite state machine, so we want to think in terms of our state. At any instance in time, what is our current state? And if I'm doing a 4-bit parallel to serial conversion, then intuitively the 4 states I'm in are either I'm idle, I have not been asked to send anything, or I'm currently sending bit 3, or I'm currently sending bit 2, or I'm currently sending bit 1, or I'm currently sending bit 0. And in this case, all we need to do is go through these states in order. I start in idle and I stay in idle until I receive a start input. The start pin goes from 0 to 1. And then I sequentially move, send bit 3, then send bit 2, then send bit 1, then send bit 0, then back to idle again. That's how we're going to implement our parallel to serial conversion operation. In any finite state machine design, we need to work out how to represent our current state. And in our case, we'll have one wire here that tells us whether we're idle or not, and we'll have 2 more wires that contain the number which corresponds to which bit we want to send. Remember, we might be sending bit 3 or bit 2 or bit 1 or bit 0, and that can be stored in these wires here. And I'm calling them wires because remember, Verilog has got its own way of doing things, but at the end of the day, data is going to be stored, well, in flip-flops or on wires. And if I have a flip-flop here with wires coming out, then when I talk about wire, I mean these wires coming out of the flip-flop that are going to hold the current state. In terms of the canonical form for writing finite state machines in Verilog, and this will be covered again in part 2 of this course, we start off with declaring our state, and we initialize the state. Our finite state machine needs to start off in a particular state to work properly, and we also declare our next state registers, because the purpose of the finite state machine is to look at our current state, to look at the current input, and to work out what the next state is going to be. And we store the next state in our next state registers. Now, all we do is we ask ourselves, if I'm in a certain state and I receive a certain input, what's my next state going to be? And I just ask that for all possible states and all possible inputs. I just go through every single possible combination there is and work out what my next state's going to be, and then I implement that in Verilog. Conceptually, it's almost that simple, and we will elaborate on this in part 2 of the course, but I'm getting you used to now the types of thinking that we go through to build the design that we're currently building. This leads us to our next state logic. We have here explicitly, depending on our current state, which is stored in these 2 wires here, and depending on our input, that determines our next state. So this is our next state logic. If we're in a certain state and we receive a certain input, how do we move to the next state? Or what next state do we move to, I should have said. This is combinational logic up here, and the reason is that it's simply a standard functional mapping. Given a certain state, given a certain input, we can have a truth table that tells us exactly what our next state is going to be. And we implement it using a case statement because it's essentially just a truth table. As well as next state logic, a finite state machine needs output logic. If we are in our current state, what should the output be? Sometimes, although we won't look at this very often in this course, sometimes we can allow the output to also depend on the current input. So in the greatest generality, the output logic is simply saying, if I'm currently in this state and the inputs are currently this, what should my output be? And again, that's just a truth table we can write down, and then we implement it in Verilog and it comes out as combinational logic. Most of the time, our output is just going to depend on the current state. This is sort of a nicer state of affairs to be in, and we'll worry about this in part 2 of the course. But that means our output logic is essentially just saying, if I'm in this current state, what is my output? Here's our output logic. The key point is that it is combinational logic, and it's just looking at our current state, and depending on the current state, that determines the output. Remember, our current state is represented by idle and bitnum, and this is just a function of idle and bitnum. Depending on our current state, we're going to have a certain output that can be described using a truth table. It's easier to write it using this inline if statement here in this particular case. And one more thing, we need to have our actual flip-flops. Our flip-flops are going to photograph the next state we want to move to at the rising edge of the clock, and so the current state gets updated at the rising edge of the clock. So in summary, a finite state machine has got our state registers for storing the current state. It's got a next state that it computes using next state logic, and it's got an output it computes using the current state. And we simply put these elements together and we get a finite state machine. Remembering, of course, we need to initialize our state at the very start. I will leave you to go through the rest of the slides and to think about this homework exercise. One favourite way people learn a programming language is by taking an existing program and then just tweaking it slightly. And so that's nowhere near as hard as having to write everything from scratch. at the same time, you have to understand what they've done in order to be able to tweak it correctly. So it's a good way of learning. So you can take my code and try to change it so that rather than have a 4-bit parallel to serial conversion, it becomes a 55-bit parallel to serial conversion chip. Last lecture we studied how to build a parallel to serial converter. Now we need to go the other way, and so we will build a serial to parallel converter, and the same objectives are as before. You want to be able to understand what's going on and implement it and make sure you understand all aspects. Another key thing we'll introduce here are timing diagrams for circuits involving flip-flops. There are at least two different but almost obvious ways of implementing serial to parallel conversion. One is to take the same finite state machine approach as we did before, but that actually leads to a more complicated hardware design. So it's easy for humans to understand, that's not a problem, but the number of logic elements used on the FPGA is going to be greater than had we taken a shortcut. And the shortcut is to use a device known as a shift register, and that provides a very simple means of doing serial to parallel conversion. Another basic building block of digital electronics are shift registers, which are simply flip-flops cascaded in this format here. It's important we understand how shift registers work. If you've ever done any coding of CPUs in assembly language or something, or even if you're an expert in C and have discovered the shift operations, then you might already be familiar with shift registers. Given a number, we might want to shift it one place to the left or one place to the right, which in binary just means adding a 0 at one end and shifting all the digits along. And basically, that's all a shift register is doing. This is explained in an embedded video here, so I'm not going to go through it here, but make sure you understand how shift registers work by going through the lecture slides yourself. Here's the said video that does two things. It explains shift registers, but it also shows you how to draw timing diagrams. Timing diagrams are very important for us to understand what's happening. VERILOG simulators at the end of the day are just computing the timing diagrams of what's happening in your circuit. And in the second part of this course, we're going to consider non-ideal combinational logic and non-ideal flip-flops, and that's going to complicate the timing diagrams slightly. So it's better that you learn timing diagrams right now for the ideal case, so you know ideally what happens, and then later when we see what actually happens, when we have to worry about delays and whatever, then you're in a good position to be able to understand and do your timing diagrams. Here I am just emphasizing yet again the canonical structure that all our VERILOG code is going to take. When we implement a finite state machine, we've got our current state, our next state, our flip-flops, our next state logic, and our output logic. Part 2 will teach you how to design things, but we're always going to implement the code in this format here. For now, you want to be able to read other people's code and notice when they use this structure here. In principle, if you've understood everything in the lectures up to now, you should be able to implement the whole design whereby one part of the FPGA generates numbers, sends it to the other part of the FPGA via parallel to serial, then serial to parallel conversion, puts it through the decoders and sends it out to the 7-segment displays. I've actually written all this for you, and that's presented in the next lecture. Lecture 11 starts with showing you my implementation of sending numbers from one part of the FPGA to the other, then displaying them. I also introduced several new features of VERILOG. So I used these features in writing my code. They are a little bit more advanced. They are there just for convenience. You can probably write the code without using them. It's just nicer being able to use these advanced features. So like with anything, first step is to be able to write code that works. Then you can try to look at how you can make your code more efficient and easier for you to write. And that's what these advanced features are doing. You can download my implementation as a Quartus archive file and just open it in Quartus. Then you can burn it to the board, look at the RTL and so forth. You can also download these individual files if you want to look at that directly. I've also embedded the code into these slides for most of these functions here as well. The video embedded here goes through the whole design for you, so you might want to watch this video. Do not write all your code at once and then see if it works or not. That's a nightmare, because chances are it's not going to work. And then where do you start with your debugging? You've got no idea where to start. It's a complete mess. Rather, you start developing things one small module at a time, check each individual module works, put two modules together, check the combination works, and build up slowly. So slow and steady wins the race. You might rush through and do your design, but when it doesn't work, it'll take hours or days to debug. If you build it up slowly from scratch, you'll save a lot of time, because when you're finished, you're finished. It's going to work, and you're going to have taken much less time than the person that rushed ahead, tried to do everything at once, and then got stuck in having to debug a big piece of code, none of it which had been tested before. Advanced feature number 1 is that we can specify parameters in a Verilog module. And the idea is that sometimes we want to have a parallel to serial converter that works with 4 bits, sometimes we want it to work with 8 bits, sometimes 16 bits. We might have a multiplexer, sometimes we want it to have 4 inputs, sometimes we want it to have 8 inputs. If we had to write a different module for every single possible number of bits, we'd go crazy. And so the way around this is by using parameters in Verilog. A good way of understanding a feature of Verilog is to try it out with an example. Here I'm having a module where I declare a parameter Fred. It's got a default value, so if I do nothing at all, then Fred's going to take the value of 2. This 70 at the end, you can ignore it. It makes no difference, except it stops Quartus giving me a warning. The reason is that in this expression here, y is an 8-bit number. Fred, by default, is going to be 32 bits. And this assignment, if I just had Fred here, it will generate a 32-bit number here, and then it will have to truncate it to 8 bits here. And when you truncate something, you're potentially losing information, and Quartus very nicely says, hey, look, you're truncating something, maybe you're losing information, maybe you'll have a very difficult to track down bug in your code. By adding this here, I'm telling it, well, actually, I know Fred up here is 32 bits, but I just want to use 8 bits of it. So 70 means I'm using the lowest 8 bits of Fred, and that means this addition is going to be 8 bits, and no truncation will occur, so no warning from Quartus. Anyway, the key point is that in this circuit here, I've got y equals x plus Fred. If I do nothing, then Fred's 2, so this module is just going to add 2 to x and store it in y. And so down here, all that this is going to do is add 2 to the input and send it to the output. On the other hand, down here, I can say, oh, hold on, make Fred equal to 5. And so now down here, y equals x plus 5, this guy here is going to be adding 5. And that's all that happens. Just think of it as a preprocessor. Just think all that happens when I do this, a friend goes into the code and everywhere replaces Fred with the number 5 and then gives it to Quartus. That's all that happens. Before Quartus runs through this, someone has replaced Fred with the number 5. If I've got .Fred 23, someone else is going to replace everything in here with 23 and then give Quartus this chip here with 23 in place, give that to Quartus and get Quartus to build that chip for me there. That's all a parameter is doing. Advanced feature number 2 is a generate block. Sometimes you need to do lots of instantiations that follow a pattern, and you can cut and paste and then edit, but it takes time, and you can maybe do that up to 16, but if you have to do it 256 times, you go crazy, and if you had to do it 2 to the power of 20, you'd go insane. So we have a generate block that does things for us automatically. Again, we think of this as a preprocessor. So it is as if you wrote everything out by hand, but you're specifying an algorithm for doing it, so you don't actually have to write it all out by hand. Of course, we don't actually do this in practice, but to explain how generate works, we're basically telling Verilog to write this out 11 times, write this out 11 times, so I have 11 initial blocks here. To emphasize, by using generate here, this is equivalent to me writing out by hand 11 initial blocks. So I have initial display hello from initial block 0, then I write out another initial block, initial display hello from initial block 1, and so forth. I physically write out 11 initial blocks. That's very different from down here, where I just have a single initial block. This is a single initial block, and here is a behavioral construction that we understand just like in C programming language, where literally I do this 10 times, but there's one initial block. That's the difference here. We can have many initial blocks or one initial block. We can do the same with always statements. I can use generate to create many always blocks, or I can just use a for statement within an always block. And with a bit of experience, you'll know when to use which one. Sometimes you can do it both ways, sometimes one way is better. A common operation in digital design is accessing particular bits of a bunch of wires. So I might have a cable with 24 wires in it, and sometimes I want to access the first 4 bits, sometimes I want to access 3 bits somewhere in the middle or whatever. And we can access bits simply by using this notation here. But in terms of making it easier for a human to read, the Verilog standard allows for an additional feature. We can have either minus colon, or if we scroll down below it, you'll see there's actually a plus colon in there. And hopefully this code's self-explanatory. Go through it, make sure you understand it. As always, ask me questions if you don't. The rest of this lecture just goes through the code in even more detail. So I have a video where I went through the code. Now I'm going through it in the lecture slides for you. And once you get to the end of that, then we have our next checkpoint, checkpoint number 3. Lecture 12 attempts to link this course to reality. If you want to build a robot, you might decide that the brains of the robot is going to be implemented in an FPGA, but you're also going to purchase other devices that you'll wire up to the FPGA. You're going to get some sensors so that the robot knows where it is. It can detect obstacles. Maybe you want it to be able to detect the environment, such as the temperature and the humidity and so forth. And you need to be able to make the robot move, so you need to be able to send signals to the stepper motors, or more generally, you need actuators. So we want to understand how an FPGA can be wired up to sensors and actuators so that it can actually do something useful in the real world. Perhaps it's worth emphasizing that even though this course has chosen to use FPGAs, and for good reason, and therefore we need Verilog to be able to configure the FPGAs, digital systems can be done without using FPGAs at all. We could do it the old-fashioned way, just using logic gates. We could do it using DSP chips. We could do it using microcontrollers. And so a large part of this course is about digital systems and not specifically limited to FPGAs. So we use FPGAs to implement it, but the same principles would work if you were to do digital systems using microcontrollers or DSP chips. As mentioned before, digital systems are used for communicating information and processing information. One reason for needing to communicate is we need to be able to talk to the sensors and actuators to find out the measurements and then to take actions. Here's an example of an actuator. It's a servo motor, so that can be used to steer our robot left or right if we so desire. How can an FPGA steer our robot? Well, it has to send commands to the stepper motor. It turns out that this stepper motor is controlled by using what's known as pulse width modulation. And you can click on the link if you want more information. It's not too important right now. Instead, let's have a look and see if we can buy a controller for it that we can connect up our FPGA to. So after a bit more clicking around the website, we found this servo controller board. So the server gets plugged into this board, and on this board there's probably a little microcontroller chip too, and that allows us to send it commands in a more convenient format, and this little board here will convert it into the pulse width modulation needed to drive the stepper motor. So a key point here is that rather than our FPGA having to do the low-level pulse width modulation, for a few dollars we can buy another board that accepts higher level commands and translates it into pulse width modulation. Another area you see this is in cars. I read the other day that a modern car probably has 100 microcontrollers around it. So instead of having a single central device that has to control everything at low levels, instead every small device around the car has got its own microprocessor that allows it to receive higher level instructions. So our central computer just needs to send higher level instructions to the various microcontrollers, and they convert those higher level instructions into lower level drive signals for the actuators. Yet another key point is that when you do want to use something you buy, you need to find the datasheet for it. And thankfully we've got the internet, so that's quite easy. And looking at the datasheet will tell us how to communicate with our device. For this particular controller chip, then we use what's known as the I2C communication standard, which is a fancy serial form of communication, which we don't need to go into, but it's just enough to know that there's a standard form of communication that we use to communicate with this particular controller here. Note that the controller itself is a digital system, and just like we were talking about before with the car example, very often you've got a central digital device communicating with a whole lot of peripheral digital systems. Here's another peripheral. It can measure the temperature and humidity for us. You are encouraged to actually look through the provided material, get a sense for, if I actually had to use this in a student project, how would I go about doing it? And then you'll start to see the relevance of digital systems to building things in the real world. We will look in a bit more detail at this particular sensor, which is used for measuring distance. It sends out a burst of ultrasonic sound waves, and it measures the time it takes to receive that burst of ultrasonic sound, and given the time between sending the pulse and receiving the pulse, that gets translated into a distance. How far away is the robot from whatever is reflecting those ultrasonic waves? As always, we need to look at the data sheet to figure out what's going on, and as is typical, sometimes the data sheet is incomplete or confusing or whatever. In this particular case, it looks like signal is just a single wire, but in fact it's two different things. The initiate goes out on one part of it and the echo back comes back on a different pin. And this one here represents the fact that we're going to get a burst of ultrasonic sound being sent out, and then the formula here tells us that to work out the distance away, we need to work out how long this pulse is in microseconds and then divide by 58 to get the distance in centimeters. We want to write some Verilog code to interact with this sensor, so we're building a robot. It's going to be powered by an FPGA, and the FPGA is going to be connected to this ultrasonic sensor, and we need to be able to get readings from this ultrasonic sensor. So our FPGA needs to be able to communicate with the sensor, telling it to take a measurement and reading back the response to find that out. Before we do this, we need to agree on the interface, our internal interface of our Verilog code. So we are going to be building a chip inside the FPGA. That chip is going to interface On one side of it, it will interface with this ultrasonic detector. On the other side, it's going to interact with our other circuitry inside our FPGA. So how do we want our other circuitry to interact with our chip? So we need to figure that out first before we go any further. Based on that, we come up with a proposed interface. Then we start thinking in terms of finite state machines. What are our states going to be? And we have a first guess. It is a first guess. It's going to change a little bit later on, but we start off with a first guess and then start writing. Again, we don't write all of it at once. We break it up into smaller parts. The first thing to do is just to be able to get our sensor to send out a burst of ultrasonic sound, and so that means we have to implement the sending of a pulse. We ignore any echo that comes back. We just want to be able to send a pulse. According to the data sheet, the pulse needs to be of duration 10 microseconds. How do we measure time? Well, that's what our clock is for. We've got a 50 megahertz clock, so 10 microseconds corresponds to 500 cycles of the clock. So in the language of finite state machines, I have to send 500 ones. Now, to emphasize yet again, that doesn't mean I send a 1, 0, 1, 0, 1, 0 or anything. No, it's a continuous one. Continuously, I have a 1 going out for 10 microseconds, but its duration is for 500 cycles. And because we like to think in terms of what's happening at the rising edge of the clock, we explain it as humans as we're sending 500 ones, even though it is just a continuous one being sent for 10 microseconds. The rest of the code and the derivation I'm not going to go through here, but again, it's a really good exercise for you to go through this carefully. It's a more complicated design example. It's the most complicated example in part 1. You're not expected to be able to do it yourselves. You should be able to understand what's happening. You should look for any mistakes anywhere, because I wrote this quickly and I did not check it myself. And the key point is that you really want to think that yes, I can take an FPGA, I can interface it to something I've bought, and I can actually build something useful. That's the key point of this lecture here, to get that point across. It might be that this last example was a bit harder for you to see what was going on. And this is a fundamental fact. It's a lot harder to understand someone else's code. And in fact, you'll find it's actually hard to understand your own code if you come back to it a year later. And so this motivates having some sort of graphical representation of finite state machines that makes it a lot easier to understand what a finite state machine is doing. And that's exactly going to be what we're going to look at when we start part 2 of this course. The last lecture of part 1 can almost be labelled miscellaneous. There are 2 things we haven't discussed yet. One is to do with pipelines and pipelining, and the other is to do with having to use a synchronizer when we cross clock domains. If the input to a flip-flop changes just as it takes a photograph, that is just at the rising edge of the clock, then the output of the flip-flop might enter what we call a metastable state, which is just a fancy way of saying that the flip-flop gets stuck halfway between a logic 0 and a logic 1. Now that flip-flop will get itself unstuck, but the problem is when it's stuck in that state, the output of that flip-flop is driving other circuitry, and it might cause problems for that other circuit. We're not going to be getting the correct calculations because we don't have the correct number going into it. So we need to try to avoid this from happening. Interestingly, it's impossible to avoid it always, but we can reduce the probability of something bad happening to such a small number that we can essentially say it's not going to happen. The way we do this is we simply put in any external signal through a synchronizer, which looks just like a shift register. Now, a shift register, we often care about the outputs of the individual flip-flops. For a synchronizer, we don't. In fact, we do not want to look at the outputs of the early on flip-flops because they might be in a metastable state. By having a cascaded series of flip-flops, each flip-flop is protecting the flip-flops behind it from entering into a metastable state. The exact functioning of what happens will be discussed in part 2 of this course. We can look at LT-SPICE simulations of a flip-flop getting stuck in a metastable state, so it will no longer be mysterious. But if you like to think in terms of analogies, think of a signal coming in as a big rock, and the closer that signal is to changing at the rising edge of the clock, the bigger that rock is. And each of our flip-flops are a wall. And if we've got a big rock coming in, it might smash through the first wall, but that first wall takes away a lot of the energy from that pulse, from that rock. And so it's unlikely that that rock that started off as being big and fast, it smashed through the first wall, our first flip-flop, but it ran out of energy to get through the second flip-flop. And if we need extra levels of protection, we can add a third flip-flop and a fourth flip-flop. And each of these flip-flops are absorbing the incoming damage from the input changing too close to the rising edge of the clock and protecting the flip-flops behind them. Of course, that's just an analogy. Once we understand exactly what's going on, you'll see that analogy is not too bad, but of course it's going to sound mysterious when presented in this way. For people that are perfectionists, it's extremely unsatisfying that bad things can still happen. And so we need to think about this in the right perspective. If we can reduce the chance of something bad to happening to lower than the chance that the Earth gets struck by a meteorite and destroys our circuit, we can't be unhappy about that. So bad things are always going to happen, power surges, meteorite strikes, who knows what. Engineering is simply about reducing the chance of failure to an acceptable amount, and that's all we can ask for. A caveat though, if we calculate, and Quartus will do this calculation for us if we so desire, and we don't really worry about that in this course anyway, but imagine we're doing this properly and we calculate the chance of failure is once every million years. Is that good or bad? And one determining factor is how many devices we have out there. If I've just made one device for my own personal use, then if it only breaks down once every million years, I should be happy with that. But if I've made 1 million devices and sold them to 1 million people, that means once a year, once a year, at least one customer is likely to have experienced a failure. And is that acceptable or not? Will that give my brand a bad name or not? If my FPGA is inside a car serving an important purpose, could it have caused an accident or whatever? So the chance of failure has to be weighed up by how many devices there are and what are the consequences of failure. For a single wire coming in from an external source, we just put it through a synchronizer and everything should be okay. If we have multiple wires coming in, and if we depend on understanding the number carried by those multiple wires, then we can't just put each wire through a synchronizer. And this will be explained in an embedded video in the lecture slides. But basically the problem is that each synchronizer can introduce an additional delay. So sometimes the output responds within a certain time period. Other times it responds within that time period plus an additional clock cycle. And if we're synchronizing multiple wires, and if some wires get delayed by a clock period longer than other wires, then the information can get jumbled up, and that can cause serious problems. So if we have multiple wires coming in, we do not simply put them all through double flip-flop synchronizers to synchronize them if we rely on the information across all the wires being in a consistent state. There are a number of ways around this. The slides, if you click the down arrow, explain one protocol for avoiding it. The embedded video a bit later on explains the danger of having multiple wires and trying to synchronize each one individually. And there are even more advanced ways of dealing with the problem, such as using what's known as a FIFO buffer, first in, first out. The main thing though is you want to be very comfortable in drawing the timing diagram for a synchronizer, including what happens if a flip-flop were to enter a metastable state. And that's explained in this embedded video here. That brings us to the second part of this lecture, and that's about pipelines. And this is a choice of implementation to try to improve the throughput of our number processing abilities. So remember, by and large, all we are doing is processing a stream of numbers. Numbers come in, we have to operate on them. We have to produce an output. And how many numbers can we process a second? Well, that's the throughput. So if I have to take, it's a bit like being in primary school and having to do maths exercises. How many exercises can you do per second? How many numbers can we process? Maybe we have to take the square roots of all the numbers coming in. How fast can we do that? And we have design considerations to make. We could just have lots of workers. If I have to process lots of numbers per second, well, I can recreate my circuit 100 times, and so I can be 100 times faster. But that comes at a cost of having to use 100 times more logic elements. That comes at the cost of having to buy a bigger FPGA, etc. So besides the brute force approach of going parallel, is there some way I can process more numbers per second? And the trick is to use something known as a pipeline, which we think of as an assembly line. I just happened to choose this as an example, probably not one of my better examples, but let's assume that a number coming in, we have to compute this particular polynomial. The fact that it's a Chebyshev polynomial doesn't really matter. You can ignore that, not really part of the course. But we've got numbers coming in. We have to do this operation here. It's also an excuse for me to sneak in just to extend your knowledge, not really a part of this course. The fact that we can also work with floating point numbers. So x can be a floating point number, just like in the C programming language. That can be represented using, for example, 32 bits. You can find out how if you're really keen by Googling. And we can implement various Verilog modules that are able to perform floating point operations in here. So I'll talk a bit about that just to extend your knowledge. It's not really a part of this course. So we're simply going to appreciate that we can do floating point arithmetic. We do need to write the Verilog code to do that, but we don't need to write our own code. We can just borrow code written by others. In software, we talk about software libraries. We use someone else's library rather than using our own. The corresponding terminology for FPGAs is using IP cores. So if I want to implement floating point arithmetic, I can actually go to the OpenCores project and grab their Verilog code for a floating point unit. That's one way of doing it. I could also pay a licensing fee to Altera, that's now Intel, and they will also give me IP cores to do many things, including floating point arithmetic. However, that said and done, the focus here is on pipelining. So the real question is, we have to apply some complicated polynomial to a stream of numbers. How can we do this so that I can process more numbers per second than had I just simply done an all-at-once approach where a number comes in, I apply that polynomial, the number goes out. Can we do it faster, but without replicating our circuit 100 times? Of course, we can do it faster by having 100 workers, but can we do it using the same number of workers per number processed? And notice how I normalized it by per number processed, because what we're going to do is we're going to use 3 workers, for example, but each worker is only going to do a third of the job. So we don't have to increase the salaries or anything. We still get the same amount of labor done per number coming in. The solution is to use pipelining, which is just like an assembly line. So rather than one worker compute the whole polynomial, we break the problem up. The first worker computes a part of the polynomial, then passes the result onto the second worker to produce the second part of the polynomial. and this frees up the first worker to then start on the next number. So in this way, we can clock through many more numbers per second than had we not taken a pipelining approach. The key point about pipelining is that we improve the throughput, but almost always trading off latency. So the latency is what we measure when we look at a particular number coming in. If a particular number comes in, how long does it take before that particular number has been processed? And that length of time is the latency. And when you have an assembly line, that latency normally gets worse, because the assembly line can only be moved along when each of the individual workers has finished doing his or her job. So the assembly line is limited by the slowest worker, and this can have an effect of actually increasing the latency. But very often we don't really care about the latency so much. We care about how many numbers we can process a second, and that's the throughput. And the more stages we add to our pipeline, then the more numbers we can process per second. We can really increase the throughput of our system. I mentioned earlier we could also just process things in parallel rather than have one person do all the computation. I can get 3 people doing all the computations in parallel. There is a trade-off though. If we go parallel, we're using more logic elements, and that costs money. If we use pipelining, we can improve throughput, but latency suffers. So parallel processing improves throughput, but we use more logic elements. Pipelining improves throughput also, but increases the latency, but it doesn't really affect the number of logic elements used. Yes, we need a few more, but nothing significantly so in most cases. And that brings us to the end of part 1 of this course. As a super quick summary, we started looking at logic gates and combinational logic and how to write that in VERILOG. We then learned a bit more VERILOG code. We looked at the hardware architecture of FPGAs. We then moved on to flip-flops, which completes the picture of digital systems. Combinational logic combined with flip-flops gives us everything. With flip-flops comes clocks. We looked at basic building blocks of digital systems, counters, converters, etc. We had VERILOG code to get you comfortable with looking at how to write VERILOG and how to implement digital systems. And we also looked at the real world, how we can connect our FPGA up to actual sensors and actuators. And then we rounded off part 1 by mentioning some advanced facts with synchronizing when we cross clock domains and pipelining to improve throughput.